All right, so 4.7, today we're taking a look at one of the other applications that we have for derivatives. And so before break, one of the sections that you looked at was 4.1, which was something called related rates. And so I do want to sort of write a little note about related rates here at the top, right? But section 4.1 is something we call related rates. And in the related rates, we saw a lot of word problems. And so the reason why I want to bring that up is because 4.7 actually also has a lot of word problems. And so it's important when we're looking at the word problems to think about clues that tell us, am I going to be looking at related rates or am I going to be using applied optimization? And so going back to that idea of decision making, thinking about some clues. And so I'm wondering, based on the related rates, what's one thing that we saw in all of the related rates problems? And it could be a notation, it could be a word in the problem, but I'm wondering what words or clues we saw that said, hey, we should be using related rates. And so I know this was like almost 2 weeks ago at this point, but if we can sort of maybe look back at our last quiz or dig back into our notes for 4.1, what are some clues that we saw that said we should use related rates? All right, I'm seeing a couple answers pop into that chat. I'll give folks a little bit more time. I know it's a Monday morning after spring break. What are some clues? All right, so I've got a couple ideas here, and we'll sort of write those out and come back later and see like which ones of these might be relevant to that, right? Because I think sometimes when we're looking for patterns, it's harder if we haven't seen something to compare it to. But a few ideas that I've seen come into the chat are looking at multiple variables. So maybe this is the clue. Constant versus increasing. And another one that came through is something is relation to time, okay? And so these are the ideas we have right now. 4.1 maybe had us working with multiple variables, constant versus increasing, and relation over time or relation to time. And so we'll come back at the after we take a look at some of these optimization problems and see which one of these are going to tell us we should be using the techniques we're going to see in applied optimization, and which ones are we going to use, or what clues are going to tell us that we should actually be using related rates, okay? All right, so let's go back to some things that we know. All right, what do we know? One of the things that we've seen quite often, phrases we've seen, is something called horizontal tangent lines. And so I'm wondering if you can tell me what's so special about a horizontal tangent line. Nice, nice. It does in fact mean a slope of 0, okay? And so that's something that if we we don't quite have that in our brains yet, we really want to take a look at this and like think about how we can get that to be sticky for us, right? So horizontal tangent line means we're looking for the slope equal to 0, which for us means we're really looking at when that derivative equals 0. Okay, so slope equals 0 means we're looking for the derivative to equal 0. Now, if I were to draw a picture of something that might have a slope of 0, maybe I could draw something like this, right? And we would know that at the very top, that x value has a slope of 0. And what's another way that I could draw something that had a slope of 0? What's another way that I could draw something that has a slope of 0? I'm thinking more visually. Like I have one example here of a picture where the slope is 0, right? And the slope is 0 at the top. Or, yeah, what if we did something as simple as have like a U situation? And now we have a slope of 0 at the bottom, okay? Something like this kind of point in particular, we might refer to as a maximum. And how might we refer to the other picture that we have here? Yeah, we could have this as a minimum. Okay, so if we have a maximum or we have a minimum, we know that the slope there is 0. It means that we have a horizontal tangent line there, okay? Now hang on to that thought because that's going to be important for today. And now let's think about what's going to be new, okay? So what's new? How do we find the maximum or minimum of a desired quantity? In other words, someone walks up to you on the street and says, I have this problem and I'd like to find out where it has a maximum. We could help that person out by saying, hey, the maximum always has a slope of 0, which means that the first derivative is equal to 0. And that's going to be true when we have a maximum, right? What if someone else walked up to you on the street and say, hey, I have a sort of different problem and I would like to find out where it has a minimum? Could you have them do the same thing that you told the person who was looking for the maximum, or would you need a different strategy? What do we think? Same strategy or different strategy? Yeah, indeed. Whether I say I want to find a maximum or I want to find a minimum, if we think back to this picture we had on the other side, both ways that slope is going to be 0 at that point, right? So it turns out that for both of these, maximum or minimum, we can set that derivative equal to 0 and solve for x. So this strategy that we've been sort of working on, for a good chunk of the semester where I'm like, okay, like we have this horizontal tangent, let's take that derivative, set the derivative equal to 0 and solve for x, is actually going to be the same strategy we use when we're looking at something called applied optimization problems, okay? And so I want to take a moment to just draw sort of like a summary picture, if you will, in this concept box below, all right? And in this concept, we're also going to plant some seeds for things that we're going to look at later this week and early next week. Okay, so a lot of these concepts here, the storyline is actually very much the same, but we need to think about like when we're going to use each tool. Okay. And so in not so exciting fashion, I'm going to draw a function. They all sort of look the same, but in this case, we'll have our f of x function. All right. And in this function, how many maximums do I have? All right, one maximum, great. And how many minimums do we have? Yeah, also one, right? We have one maximum, we have one minimum, and it turns out that our maximum might be somewhere along here, like the highest point on that curve. And it does, in fact, have a slope of 0. So we could say here that our f prime of x equals 0, right? And additionally, we do have that one minimum in the green down here. And it does, in fact, have f prime of x equal to 0 as well, okay? So that's going to be sort of the important part for us today, right? That at a maximum, we have a slope of 0. At a minimum, we have a slope of 0. But I'm wondering if someone can tell me what the slope is to the left of this maximum point. Someone said, describe to me the slope on the left-hand side. This part right here. Yeah, we don't know what they are. We don't know an exact number for it. Like we can't say the slope is 2. We can't say the slope is 15. We don't know. But we do know that it's going to be positive, right? So we might even say over here that f prime of x is positive, right? Where else on this graph could I say that the slope is positive? Very right. Yeah, the right side of the green, precisely. So this region also has a slope that is positive. We don't know what it is, but we know it's positive, all right? What about the section of the graph that goes between the pink dot and the green dot? What would we say about that f prime or that slope? Yeah, that slope in that middle region is indeed going to be negative, okay? I'll make that circle around the minus sign extra big so we don't think that it's a theta, but it is indeed saying that that slope there is negative, okay? All right, so Again, the key points for today are that this maximum and a minimum have a slope of 0. But later on this week, we're going to be talking about like, how do we tell the difference between whether it's a maximum or a minimum? Okay, and so that's where knowing the slopes on the different sides are actually going to come into play. All right. All right, so let's take a little detour into reminding ourselves about some geometry, okay? So some useful formulas, all right? I find that for folks, geometry, sometimes again, it's the vocabulary. Maybe we don't really remember like what the vocabulary means. And so I wanna do a quick review about 3 concepts, all right? So in particular, let's talk about something called perimeter, right? We're talking about perimeter. We're going to talk about area, and we're going to talk about volume. Okay, so perimeter, area, and volume. Concepts that we have seen at some point in our academic career. And so I'm wondering if we can take a moment and using one phrase, all right, using one phrase, I'd like us to explain what we think perimeter means. Right, so take 30 seconds, type something into a chat. Don't hit enter yet. All right, so we'll sort of give everyone some think time, but we'll type our answers in. What phrase makes us think of perimeter? Okay. All right, so I'm going to have you go ahead and hit enter. What phrase helps you think about perimeter? All right. All right, awesome. Let's go ahead and read through some of these. So I see things like the length around something, the continuous line of a figure, the outer edge, the combined length of the sides, the distance around the object, the outside, adding all the sides together, the length of a line to encompass an object, and we add all the sides. All right, and so what I'm seeing here is a mix of like the concept and the procedure, right? So the concept of perimeter is exactly saying like, what is the distance around the object? All right, so I see that Jordan has put here the distance around the object, or other Jordan has said outer edge. And I like both of those because they're really indicating that we're looking for that concept, right? We're looking for the distance around the object. And so maybe let's go ahead and put that one down for perimeter. So the distance around an object. All right, great. And procedurally, okay, so that's the concept, but the procedure, really like what some of us have said, like Raylene and Noor have said, that we add all the sides together, all right? And so that is precisely what we do. We add all the sides together because we're looking for the distance around an object, all right? So distance around an object, and we go ahead and we add all the sides. All right. So before we write down any formulas here, all right, I'd like us to do the same thing with area. So take 30 seconds, in the chat, type what you think the concept of area is. All right, what do you think the concept of area is? And if you're not sure, but you maybe know what the procedure is, you could type that in as well. Okay, so now we're going to sort of ask ourselves the same question, but not for perimeter, but for area. Okay. All right, so go ahead and hit enter. Let's see what we have for area. Love it, love it. All right, so let's take a read through these. I see multiply the sides, the space inside something or a shape in 2-dimension. All right, that's pretty specific. The size of the surface of an object, the total surface space of an object covered, the total space within a shape or an object, amount of flat space taken up, the total amount of space a 2D shape takes up. Great. All right. I'm seeing one sort of phrase consistently, which is 2-dimension. And I think that's pretty key here. All right. So when we're looking for area, we are indeed looking for the space inside a 2D object. All right. And so when we have all of our formulas, what they're telling us is the amount of space inside of a 2-dimensional object, okay? Inside a 2-dimensional object. Great, all right. So let's think about how could we describe volume, okay? So again, let's take a short period of time, think for ourselves, type into our chat what we think volume is conceptually. All right, so take a moment to look up that, and then we'll go back in and fill in all these formulas, okay? Because as important as it is to remember the formulas, it's also important to think about like, well, when am I going to use which one, okay? So we're typing, what is volume as a concept? Right, and when you feel ready, go ahead and hit enter. Yeah, there we go, right? So we can almost modify what we have for area. Area is how we describe the amount of space inside a 2D object, but volume is actually the space inside of a 3D object. Okay, and so knowing what these concepts are, knowing what these concepts are is going to be really important as we think about like, how do we decide which formula, okay? All right, so let's actually start with the volume formulas. We'll talk through a couple that tend to come up pretty quick or pretty frequently, and then we'll go back and look at area, and then we'll write down some formulas for perimeter. Okay, now some of these may not have really nice formulas, but if you know the concept, the formula will actually come from that. Okay, so let's start with volume. Some of the ones that can be a little trickier. So one shape that we often find the volume of, or we're asked to find the volume of, is the volume of, what shape is that?
Cylinder.
Yeah, that is indeed a cylinder, okay? So the volume of a cylinder. And now a cylinder if I were to cut sort of this way, like across the cylinder, what shape would I have? If you just took slices of your cylinder, what shape would you have? All right, I see one rectangle. And now to be really precise, I mean that we're cutting this way across. Okay, so if I were to just slice part of this as thin as it could be, it would indeed be a circle, okay? If I cut this and I'm sort of looking at the two different parts, yeah, I agree we have two cylinders. But at the base of it, at the base of it, at the root of it, what we're really looking for is we actually have a bunch of really thin circles that we're just stacking up to a certain height, okay? And so this formula is actually going to be pi r squared. That part should look familiar. Pi r squared. What does pi r squared tell us?
The area of a circle.
Yeah, the area of a circle. So if we take the area of a circle and we stack it all the way up to the height we want, or we multiply by the height, we get the volume of a cylinder, okay? Another common shape that we see that we're asked to find the volume of is a cone, right? So the volume of a cone. Now it turns out that the volume of the cone is actually related to the volume of a cylinder. And as much as we would like it to be half of a cylinder, it turns out that it's pi r squared h. So that part is just like the cylinder, but it turns out that 3 cones can fit inside of one cylinder. And so that's why we have a 1/3 in front, because we're going to take, if we had 3 cylinders and we filled them up with sand and then we poured those 3 cones worth into the cylinder, we would actually fill that space exactly. Okay. So very similar, but the thing with the pointy part, the cone, has the 1/3. Okay. All right, one more common shape we see. All right, so we have the volume of a, what shape is this? It is not a rectangle. Close. All right. We wouldn't call this a rectangle because a rectangle is in only 2 dimensions, right? But Enrique adds one word to the end, which is it's a rectangular prism. And now we have the name of the shape. Okay. So a rectangular prism, kind of thinking like it looks like a tissue box or something like that. All right. What is the volume formula for a rectangular prism? Yeah, length times width times height. Okay, so we have our length, times the width times the height, right? And that will indeed give us the volume, all right? Now, real quick, I have in all of these, I know that they're volume because we have radius times height. That gives us 3 dimensions. Here I have radius times height. which gives us 3 dimensions. And here I have length times width times height, which also gives us 3 dimensions. And so it should make sense that if you're looking for volume, you have sort of 3 variables that you're looking at, all right? So something that gets you 3 dimensions at the end. All right, so let's hop back 1 dimension. And let's take a look at area, all right? And we'll sort of run through a list of common shapes like we did for volume, okay? And so let's start off with the area of a circle. And circle is 2 dimension. And I think we mentioned this earlier, but the area formula for the circle is
pi r squared.
yeah, pi r squared. Great. So we have pi r squared, and that is our area formula. And we know it's the area because we have radius times radius. That's going to give us 2 dimensions. What about the area of just a regular rectangle? So not a rectangular prism because that's 3 dimensions, but a rectangle.
Is it length times width?
It sure is. Nice. So we've got length times width. And just like in our area of the circle, we see 2 variables, which tells us we're working in 2 dimensions. Okay. Now, every once in a while, we actually take sort of a 3D object and we look at just the space around the outside. And we call that surface area, right? So instead of looking at a 3D shape, but how much space is inside, we look at a 3D shape and we think about how much space is around the outer edge, okay? And so one formula in particular that tends to come up is looking at the surface area of a cylinder, okay? Surface area of a cylinder. Now, if you were to describe to me the shapes that make the outer parts of a cylinder, what shapes would you say? Great, exactly. We do indeed have sort of the top and bottom. If you're thinking about this like a soup can or yeah, any sort of like cylindrical shape, like a can, a water bottle, something like that, you're gonna have 2 circles, right? 1 circle on the top, 1 circle on the bottom, plus if you've ever peeled off the label on a soup can and like gotten it all off on one piece, you might realize that it's actually just a rectangle, okay? And so we have 2 circles and a rectangle. And so we can actually borrow some of our area formulas from before to help us make this surface area formula, all right? So I have 2 circles. What's the area of a circle? I just said this earlier. What's the area formula for a circle? Yeah, pi r squared. So we have two of these. So 2 times pi r squared. That tells us in a formula that we have 2 circles that we're adding. Okay. Now for the rectangle piece, I'm actually going to draw a little picture off to the side. All right. So if you unwrap the label of a can, you end up with a rectangle. Okay. Now the can has a certain height, and so this side we would label as H. If I were to roll this back up or put this back on the can, what does this part represent on my can? Yeah, if I roll this back up, all right, if I roll this back up like I were trying to make a paper towel tube, I would in fact get the circle that is part of the can. Now, Dallas says perimeter of a circle. We don't usually say perimeter for circle, but it is actually perimeter. What's the word we tend to use instead of perimeter when we're talking about a circle?
Circumference.
Yeah, the circumference, right? So this top part is actually the circumference of the circle. What's the formula for circumference of a circle?
Is it something with the radius
It is
and the
something with
length of the radius? God, it's been so long.
Yep.
I feel like these are the most easiest formulas that everyone forgets.
There we go.
There
So
you
this
go,
is
2 pi r.
2 pi r, okay? How many variables are in this? When I look at that equation, 2 pi r, how many variables are there? Yeah, there's only one, right? Just the radius. But how do I find the area of this shape? Yeah, we multiply them together, right? This is our length times width. And so for the one rectangle, we'll have 2 pi r times h. Okay, so when you see this surface area formula for a cylinder, it looks pretty complicated, but it boils down to having 2 circles plus 1 rectangle. Okay, 2 circles and 1 rectangle. So our 2 circles give us this, and our 1 rectangle, excuse me, our 1 rectangle gives us this. All right, so we've talked about volume. Every formula that we had in our volume had 3 variables. And if we look at all the ones for our area, we have 2 variables, 2 variables, 2, 2. So everything is in 2 dimensions, okay? Now let's revisit this idea of perimeter. It says that this is a distance around our object. And in fact, we're looking at 1 dimension here, okay? And so I would say for pretty much any shape, you're just going to add all the sides together, however many sides you need in that shape. The one special formula that I think we should write down is that circumference of a circle, and we're going to go with 2 pi r for that formula, okay? It's not wrong to say pi times the diameter, but what we're going to find is that we actually will be able to write more formulas with the radius, so it would probably be more valuable to remember that formula. okay? All right, so we've got ourselves a bunch of formulas. All of this is geometry. If these don't feel familiar to you, I would suggest making some flashcards and really getting these in your brain so that as you're working on things, you don't have to keep flipping back and forth to like, oh, what is this formula? What is that formula? Okay. All right, so it's I think our time for a break. When we come back, we'll walk through some of these practice problems, all right? And one of the things we're gonna find is that sometimes we'll be able to choose a formula off this list, and sometimes we'll have to modify this formula a little bit, okay? And so that's sort of going to be the game that we need to play, is how do we think about what that formula is, and what might be useful for us to help us pick the formula. Okay, there's going to be lots of algebra too, but at the end of the day, the derivatives are actually going to be way easier than some of the derivatives we saw on that last exam. Okay, so good news is the derivatives part are easier. The bad news is we still got to work with our algebra and our geometry. Okay, so it is 10:22 right now. Let's be back at 35, and I will see you folks back at then. All right, folks, welcome back from break. We're going to take a look at some practice problems as promised. All right, so we've looked at some concepts, some important formulas. We know that we're looking for maximum and minimum points. And we talked about how to do that, all that goes back to is that idea of horizontal tangents that we've been talking about for much of the semester. And we're going to take that, and we're also going to look at some formulas like geometrically and thinking about how we use those to help us find what we want to find, okay? So we're going to start off today with example number 1. All right, this is a very classic kind of problem, but I really want us to be thinking about decisions as we sort of go through this, okay? So not just trying to memorize the procedure, like I'm gonna sit and write the procedure 20 different times and then I've got it, but thinking about like, why are we making decisions along the way, okay? So we have this example. A rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other 3 sides. Given 200 feet of wire fencing, determine the dimensions that would create a garden of maximum area. Then determine the maximum area, okay? And so my suggestion for doing any of these kinds of problems is always to start with a diagram, okay? So starting with a diagram, I think, is going to be really useful for us. And after we have a diagram, I like to do a little formula brain dump, okay? Now, the first step, I think folks are usually like, all right, I'll draw a picture. But the second step, asking you to sort of write down as many formulas as you think that we might possibly need and which ones might be relevant, that can feel scary for people because I think it's something we often try and do in our heads. And I'm asking us to just really put that thinking out there on paper, okay? And after we do that, so after we have our diagram, after we do our formula brain dump, then we're going to take a look at finding the maximum or the minimum, right? And that again is also going to be a choice, thinking about what is the problem asking us to find, okay? All right, so what I'd like to do is to give you about 30 seconds, maybe a minute, that seems more reasonable. Take about a minute and start thinking about the diagram, the formula brain dump, and whether we're going to find the maximum or the minimum, okay? So read through that problem again, What can you draw a picture of? What formulas from the previous page might be useful? And are we looking for the maximum or the minimum? And like, what's telling us that? Okay, so take a moment to fill in what you can for this, and then we'll kind of check that over together. Taking this time to sketch a picture. What formulas might we need? Are we looking for the maximum? Are we looking for the minimum? All right, so let's start with number 3, finding the maximum or the minimum. Which one of these do we think that we're finding in this particular question, the maximum or the minimum? All right, I see Ian has put in here that we're looking for the maximum. Yeah, all right, we are indeed looking for the maximum. And how did we know that? Like, what in the problem told us we were looking for the maximum? It's not a trick question.
Literally says it in the
Yeah, it literally says find the maximum area, right? Find the maximum area, find the maximum area. So we're finding the maximum. What other words might someone use in the word problem instead of maximum that would still tell us to find the maximum? In other words, what are some synonyms they could have used there? Exactly, right? So the problem might say, create a garden of the largest area, create a garden that has the most area, but all of those clues would tell us that we were looking for the maximum, okay? So thinking about, in this case, it's very straightforward. It says find the maximum, but sometimes we might substitute that for other words that mean the same thing, like largest or most, okay? All right, so formula brain dump. What formulas come to mind when we're thinking about what might be useful in this question?
length and the width.
Okay, so those are variables. What is the whole formula? Or rather, what is the equation? Right, for an equation, we're gonna need two sides of something. We're gonna need an equal sign. Yeah, yeah. So we could
Oh,
say,
like fully, like area of a
yeah,
rectangle. Okay, I was like, what?
yep. All right, so maybe area of a rectangle equals length times width might be important, okay? We don't wanna discount any ideas, all right? But this is a brain dump, so let's think more. What other formulas might possibly be useful in this question? All right, so we see a volume of a rectangular prism might be length times width times height. Okay, and perimeter. Okay, so perimeter of a rectangle, and what would that equation be? Great. So 2 length plus 2w. Okay, great. I'm really glad that no one said pi r squared, because we don't have, I know we haven't drawn our picture yet, but we don't have anything about a circle. So we probably don't want to use the pi r squared ones. We probably don't want to use any of the like a surface area of a cylinder. That seems like maybe it wouldn't be useful. Like volume of a cone doesn't seem useful. Same thing, volume of a cylinder doesn't seem useful, right? So these are sort of the three that have to deal with a rectangle of sorts, all right? And so maybe now if we draw a diagram, we can think about which ones we actually want to continue to use, okay? So diagram. We need to draw a rectangular garden, all right? And what is so special about this garden though, other than it's a rectangle? Like as we're designing the boundaries for this rectangle, what's important? All right, so Raylene says we don't need fencing on one of the sides. And Stefan, you're saying there's two different materials, right? So we have a rock wall on one side. And yep, if we're gonna think about like maybe cost or thinking about the length, right? The wire fencing, we only have 200 feet of it. We don't have any more. Now that 200 feet of wire fencing has to cover how many sides of this garden? Yeah, it has to cover 3 sides of the garden. Wonderful. All right, so I'm gonna draw a picture. I'm actually going to draw 2 pictures because I think both of them are valid depending on how you label your diagram, okay? And one of the hardest things when people are drawing pictures is they're like, does it have to be this way? And sometimes there's more than one option, okay? So we could draw something like this, where we have a rock wall, and then we have wire fencing. And maybe we're thinking that we're going to label the parts where we need the wire fencing. So we might call this length and call this width. And what would we label this third side here? Yeah, we would label that length, right? Now, a common question I get is like, well, which one is the length and which one is the width? And it turns out that it doesn't really matter. So if you have the same picture, but your L and your W's are switched, that's absolutely fine, okay? It also turns out it doesn't matter if your rock wall is going horizontally, or maybe you're like, no, this is the rock wall and this is my garden. That's also fine. You could draw the picture in a different orientation. That's fine. And you could label this with length and width. And again, if you put length here, you want to put length here. But if you were like, nah, this is the width, this is the length, and this is the width, that's also fine. Okay. Now, for some of us who are a little bit more boring, like myself, I like to think about them in X's and Y's, but you don't have to. But one of the things that I tend to do, and I think I do this for related rates problems as well, is anything that's horizontal, I'll label with an X. And so I would also label this one with an X, and I would call this one Y. Okay. So these are 2 different ways that you could draw your diagram. They're both correct. along with the sort of variations that we said, like maybe the length and width are switched, that would be okay. All right. So we've got a diagram, we've got a formulas to look at, and we already know that we're looking for the maximum. All right, so all of this is great. Now let's take a look at setting up our process for finding this maximum. Okay. So in general, when we are, so if we want to find the maximum area, okay, in our heads, we're like, maximum area means the top of a bump on a graph. And if we sort of rewind a little bit, that's like saying, we want to find out where this pink point is, right? We want to find out where that pink point is. How do we find that? Find our maximum by finding that derivative, setting it equal to 0, and solving for x, okay? So to remind ourselves, to find the maximum area, we are going to find f prime of x, set it equal to 0, and solve for x. All right, that's a procedure that we want to be like, oh, someone said find the maximum area. Here's what I'm going to do in 3 steps. I'm going to find my f prime, I'm going to set it equal to 0, and I'm going to solve for x. Okay, we want that to be a very immediate reaction for us. All right, so of our formulas, which one do we want to find the derivative of?
The first one.
The first one, the area one, right? We want to find the maximum area because our question said find the maximum area. They could have also said find the largest area, find the most area, but that's how we choose which equation we are going to find our derivative of, okay? All right, so let's say that we have, how do we want to do this? All right, so we have our find f prime of x, and for us, that means that we have area equals length times width, okay? What is the derivative of the left-hand side? What is the derivative of A?
F prime A.
Say that again?
F prime of A.
No, it would not be f prime of A. That would be saying that A is an x value.
That's how I actually was thinking in my head.
Since it had the full.
Okay, so an A prime, sure, we could have A prime. Okay. How would we find the derivative of the right-hand side?
Would we use a product rule?
We could use the product rule. Okay. Now, how many different variables do we have on the right-hand side?
2.
We have 2. Okay. Now, altogether, we have 3 variables. We have our area, we have our length, we have our width. And it turns out that while there are methods to find the derivative with so many variables that involve exactly what Dallas said, some sort of version of a product rule or some version of a chain rule, right? Those are fun things to look forward to when you get to Calc 3. It turns out that this right now, if we tried to solve it this way, would require multivariable calculus. Now, we are not in multivariable calculus. We are actually in single variable calculus. Okay, so for us, this is actually a problem, like an issue, that we have too many variables. Okay, so for us, this is too many variables. All right, and so what we want to do is try to get rid of one variable before taking the derivative. Right? Try to get rid of one variable before taking the derivative. That is, we need an equation that relates length and width. Okay, we need an equation that relates length and width. Right? So we've sort of encountered a situation here. We have too many variables. We have 1, 2, 3, and so far we're used to seeing questions that just have 2, usually an X and a Y, right? So the fact that we have 3, which is more than 2, is a problem for us. And so what we're going to try and do is use algebra to help us turn this equation into something that only has 2 variables, right? We're going to have an A, but we're only going to keep either the L or the W. Okay. Now, it turns out that in our formula brain dump, we actually came up with a way to help us relate something. And in talking about our picture, like how we drew our picture, that we only have wire fencing on 3 sides of it, and as Stefan astutely found out, there's only a limited amount of that wire fencing, right? We don't have an unlimited supply. We're not going back to the store to buy more. We only have a certain amount. Okay, and the fact that we only have a certain amount actually helps us figure out the relation between the length and the width. The wire fencing goes here, here, and here, right? Or if your diagram looked like the one on the right, your wire fencing went here, here, and here. Which one of those other formulas that we put in our brain dump might be useful in helping us think about how much fencing we have?
Perimeter.
Yeah, perimeter. Great. All right. So it turns out that sometimes when we're using our brain dump, and not sometimes, oftentimes, we're going to come up with the other equation that we're going to need to make our lives a little bit easier. Okay. Now, why wouldn't we use this one, the volume?
We're not looking at a 3D dimensional.
Yeah, we're not like looking for a three-dimensional, right? We're not saying like how much vertical space do the plants have to grow, right? It's not an inside situation like a greenhouse, but it's more of an outside situation where they have, in theory, unlimited vertical space, right? So, all right, how do we modify this equation to fit this picture where we only have 3 sides that use the fencing? Because in our equation, we had 2 length plus 2 width, which gives us 4 sides. But one of those sides doesn't need fencing. Yeah, we could just say instead, right? Think about what did we define perimeter as? Perimeter is we add up all the sides that we need. So in this case, we would have length plus width plus length. That's it. In other words, like Dallas said, we have 2 length and only 1 width. And that is going to equal, like Stefan says, it's going to equal 200 because that's how much fencing we have, okay? So let's sort of sneak this in over here, right? That we have 200 equals 2L plus W, right? Now in this equation, all right, we want to be really careful about our algebra here. Which letter is easier to get by itself, the L or the W?
The W is already by itself, so you could just move it over.
Great. So what does that give us?
W equals 200 minus 2L.
Great. Okay. So everywhere I see a W, I could just say it's the same thing as 200 minus 2 length, right? W can be replaced by 200 minus 2L. Well, let's try that for our equation here. Okay. Area equals length times width, but instead of writing width, I'm going to write 200 minus 2L. Okay. Now, if I were to use what we know about derivatives, okay, what rule or rules could I use to find the derivative on the right-hand side?
Chain rule.
All right, what makes you say chain rule?
There's an outside and an inside.
Okay, so are we?
Oh, wait, actually, no.
Yeah,
I would
I don't.
do product.
Okay, so we could use product rule, right? We could do that. What else could we do? Some of us in our setups for product rule, sometimes we like make some small mistakes here and there, right? So maybe, like Raylene suggests, maybe we could FOIL it out first, like pretend like we didn't even know that we had a product rule. Right, I distribute, I get 200L minus 2L squared. That looks a little bit more straightforward to take a derivative of, okay? So you could use product rule here, or you could use algebra and then turn it into something where you only need power rule, okay? All right, we found this equation now that gives us just one variable on the right-hand side and one variable on the left-hand side. So let's find that derivative, okay? I know we've been writing something like this, a prime, right, as a way to find that derivative. What would our derivative on the right-hand side be? Okay. Let me ask you a slightly different question. What if I gave you this? Now, what's that derivative?
Negative 4x.
No. Yeah, I agree with what's in the chat, right? Derivative of 200x is 200 minus 4x, right?
Sorry, I thought x equals 0 and then I multiplied it, but x actually equals 1.
Yeah. Okay, so we take that derivative. That's what it looks like when the letters are a little bit more familiar, right? That's how we were doing it before break. What's another way to write this y prime, by the way? Great, we could write this as dy dx, okay? Now, I want us to take this example in the purple, and I want us to write an equivalent statement for this derivative, right? So this 200x minus 2x squared is like our 200L minus 2L squared. So what do we get for our derivative, a prime? What does a prime equal?
(200 minus 4L).
Great, 200 minus 4L, okay? Now, just like I said, hey, we could write y prime as dy dx. How can we write a prime? Yeah, exactly. We can write it as dA dL. Okay. Why is this important? Some of us were saying we need an L prime. And they're thinking, oh, maybe we need implicit because we have this thing that might be a function. Whatever the bottom letter is, so in this case it's L, in this case it was X, whatever that bottom letter is, that's the one that we're taking the derivative with respect to. That means that anytime we take a derivative of just that letter, like the derivative of X is going to be 1, that means same thing over here, the derivative of L is just going to be 1. That's why we don't need the L prime here, okay? But our derivative of A is going to be dA dL. All right, so the variable A is like our Y and the variable L is like our X, okay? So if you prefer to write it this way, that's fine, but you also need to think about where this comes from, okay? When you were doing your related rates stuff, the 4.1 stuff from before break, what was the denominator here? Yeah, that was dt, okay? So I want to go back up to the top and make one modification for what we were talking about earlier, like how do we know if the word problem is going to be related rates or applied optimization, which is this section. And the way we tell is exactly this part. All right, something in the word problem should say something with respect to time. Something is changing over time. And when we say something is changing over time, that's why we always have the dt in the bottom. Okay. So related rates, we should see things about time, but when we're looking at applied optimization, we're going to see a lot of words like maximum or minimum, things like that. Okay. All right, so we've got our derivative here. What do we do after we find our derivative? Yeah, we want to set it equal to 0. Why are we setting it equal to 0? All right, why are we setting it equal to 0? Yeah, exactly. Because when we set it equal to 0, it's giving us the minimum or the maximum. Okay. So set things equal to 0 because we know the slope at those points is 0. We've got this. Great. Let's solve. All right. So we get L by itself. I'm going to add 4L to both sides. And I get L equals 50. And if this is all I wrote, I would lose some points for a couple of reasons. All right. What's one reason I might lose some points here if this is all I have? Yeah, those units, right? So let's go back to our word problem. What units should we put with our 50? Yeah, we're looking at 50 feet of wiring. Exactly. So length equals 50 feet. That would be part of my answer. But let's go back to the word problem again. Make sure we've answered everything it's asking for. So it says, determine the dimensions that would create a garden of maximum area. What do they mean when they say dimensions? Like I found the length, isn't that enough? No, we need the width as well, okay? And that is exactly right. When someone says dimensions, they want the length and they want the width so that they basically have directions to go out and build this garden, right? They want you to tell them how long is that width so they know how far to measure out, okay? So we're gonna need the length, or we have the length, we wanna find the width. What else do we need to do in order to find our full answer?
Are we able to do the same thing that we did by finding the W and plugging that in and using that formula to find now the W by changing, we did W equals 200 minus 2L. Could we do L now equals 200 minus 2W?
So I'm not really asking for a procedure right now. What I'm asking
Oh,
for is like, what else do we need in order to answer the question? Because if you just give me length and width, I argue you have not fully answered the question.
well, yeah, I don't feel like, oh.
Yeah, exactly. We need to find that area, right? So as we're answering these questions, you got to think about what your answer should look like. We need the dimensions. Like someone says, I want to know like how long I should measure that garden, how wide it should be. That's the dimensions. But then it says, determine the maximum area. That means I also want to find out like how big that garden's going to be. Okay. So we need 3 pieces of information to have our full answer. All right. So we have our length. How do we find our width? Because we need that width.
I think that's what I needed to be more specific on, was that I was saying we already had the length. Can we use that same formula to find the width? Because that's another part that we need to find, and then use those 2 information.
Exactly. So in fact, we can go back up to this formula, right? Our width equals 200 minus 2L. And so we can say width equals 200 minus 2 times 50, which should give us a width of 100 feet, all right? And when we write our dimensions, if you've ever been to Home Depot or Lowe's, something like that, they write it like something like 50 feet by, that's not a times, it's like a measurement, tells you how the 2 measurements are sort of different, right? You have your length by your width, right? You could get a little fancy and you could say, I don't want to write the letters FT, so you could say 50 feet, like 1 little apostrophe thing is feet, 2 little ones is inches. You could say 50 feet by 100 feet. That would be an alternative way to write the dimension. But how do we find our area?
Multiply both of them together.
Multiply them together, right? We know that the area of a rectangle is going to be the 50 times the 100, and so we'll get 5,000. What are our units here?
Feet squared.
Great, it's going to be feet squared. Okay. All right, so we've got our dimensions, we've got our area. We now have completed that problem, okay? So we've got our diagram, a formula brain dump, and finding that maximum minimum, all right? That is sort of the general flow of these kinds of problems. And the way we know that they're going to be related rate, or they're not related rates, and rather they're going to be applied optimization. That word optimization means we want it to be the best possible. So that might be the most area we can make with 200 square feet, 200 feet of wire. Or it might be the least amount of money we have to spend on something, right? That's also optimal in a way, right? So that's where we get this optimization. We're thinking, oh, there's going to be a maximum or a minimum because we want the best thing possible for that situation. Okay. All right. So this
Professor,
is
can I ask a question?
For sure.
The air, you know, you're like, one of your answers is area, and then you drew that picture of a rectangle. If we don't draw the picture, would you still understand what we're finding the area of, or we should be notating that?
I think that's up to you and the rest of your work and how organized it is. So if I can tell that you know what you're talking about.
Perfect.
All right. So I'd like to actually, oh, Dallas, go ahead.
I had a question. If we used L instead of W, would we still get the right answer, or?
I see what you're saying. Like over here, if you had like solved this one differently.
Yeah.
Yeah, your numbers likely would have, yeah, if your diagram looks like this, you should get the same answers. They might just pop out in a different order.
Okay.
Like
Thank
you
you.
might find the 100 first and then find the 50.
Okay.
I'm glad you asked that, because I was thinking that too. I'm like, can we just find the L first and then? Okay.
Yeah, for sure. And that's why I sort of asked, like, in this one, which letter is easier to solve for? Because, for example, if we had length plus width, I would assume that probably half of you would choose length and the other half would choose width, and that would be fine. If you did choose to get the L all by itself over here, maybe let's take a look at what that would look like. So if I wanted to get L by itself, I'd have 2L equals 200 minus W. And then I divide everything by 2, I'm going to get L equals 100 minus 1/2 W. I would just prefer not to work with the fraction if I can. So like this means I don't have to work with the fraction, but if you solve this way, for sure, like I don't think a 1/2 is all that bad. You know, maybe if it was like 49 over 2,501, I would choose differently, but it's up to you what you want to do in that process. All right. So the other question I want to take a look at today is example 4. Okay, you'll notice that on your Desmos assignment that there is one called Can Design, and it's going to be sort of similar in flavor to this example 4. But I want to do this problem together because I think it can look scarier than the other problems just because it has like more letters going on, but it's going to follow the same flow very closely. All right, we'll do a diagram, we'll do a formula brain dump, and we'll find either the maximum or the minimum. Okay, so scroll down to example 4. All right, so example 4. You have been asked to design a 1 liter oil can shaped like a right circular cylinder. What dimensions will use the least amount of area? Okay. So leave space for a diagram. Leave space for a formula brain dump. And leave space for finding the maximum or minimum. Okay. And so sort of same as last time, let me give you about a minute to start drawing some pictures, right? Thinking about what formulas might be useful and determining whether we're going to find the maximum or the minimum. Okay, so take a moment to do that. Let's see what we get. All right, so let's start at the bottom again, that finding the maximum or the minimum. Which one do we think we're going to be looking for in this case? And what clues tell us that? Great, all right. So we have one that we're looking for the minimum. It doesn't say minimum anywhere in the problem, except it does say least amount, and least is the opposite of most, right? So we have the minimum that we're looking for here. All right. And so what are we finding the minimum of? Like in the first example, I said we were finding the minimum area. What are we finding the minimum of here?
Material.
Okay, so what does material correspond to? Does that correspond to volume or surface area?
Surface area.
Surface area, okay. So nowhere in this problem does it say find the minimum surface area, right? It doesn't use those words exactly, but that's why when we think about like, what does area mean? What does volume mean? That helps us figure out like what we're trying to find, okay? So I would say here that we are to find the minimum surface area, all right? What's our process going to be? What are the 3 things that we want to do to find that minimum surface area?
Take the area of the 2 circles plus the 1 rectangle.
So we're trying to find the minimum surface area. What's the process for finding the minimum surface area?
Are we still finding f of prime of x?
Yep, we are. That's the start. What else do we do?
Set it equal to 0 and solve for x.
Right? Anytime we say, hey, I want to find a minimum or a maximum, these are our 3 steps, right? It's the same 3 steps as find a horizontal tangent because every max or min has a horizontal tangent, right? So these 3 steps always going to be the same. It doesn't matter what the words in the problem are. The words in the problem just help us figure out like the little nuances or the smaller steps in between. But the big picture here is going to be the same. Okay. All right. Well, I think that actually helps us with this brain dump a little bit, this formula brain dump. What might be a good equation for us to write down? All right, so maybe surface area of a cylinder, right? And we have 2 circles. This is what I think, Enrique, you were talking about. We have 2 circles plus 1 rectangle, right? 2 circles plus 1 rectangle. All right. I'm looking at a cylinder, so maybe I need volume. I don't know yet. Volume of the cylinder, we have a bunch of circles, pi r squared, and we stack them up to a certain height. So we multiply by h. Okay. All right. I'm really glad that no one said, hey, we need to use length times width because we're not looking at a rectangle. I'm really glad that no one said we're going to be using like the perimeter, right? Because we're looking very much to find that surface area. All right, so now for the diagram. I bet that if we were all in class together and looking at everyone's drawings, probably everyone's drawings would look a little bit different, all right? But at the end of the day, we should all have cylinders, right? Some of us might have a cylinder that looks like this, more like a can of tuna or something like that, right? Like sort of a shorter, fatter cylinder. And we might label that this is the radius, this is the height, okay? Some people might be like, oh, I was thinking more of like a regular soup can, right? So maybe something like this. And we have our radius, and we have our height, right? Or maybe someone was like, I think more like a straw, like something very tall and thin. This is the radius, and this is the height, right? So I think drawing all these pictures is just to say it doesn't matter. It doesn't matter how tall your cylinder is in the picture. It doesn't matter how big the radius of your cylinder is in the picture. Draw a picture of a cylinder and label it, okay? Sometimes we get scared to draw the diagram because you're like, well, but I don't know how big it is, so I can't draw the diagram. It's okay. It's just a visual, right? You can go back and change things later if you want to draw something more accurate, but as a first go, it doesn't matter so long as you have the shape correct, all right? Now, one key word in here that we didn't really talk about yet is this word right, all right? So the right circular cylinder means that like the side and the bottom or the top meet at a right angle, all right? So it means like it's not like a slanted situation, all right? So we wouldn't want to draw something like this where we have like, all right, like that would be not a right circular cylinder. So we wouldn't want to draw that last picture. But any of the other three would be fine, right? Any questions so far about our diagram, the formula brain dump, or finding the max or the min?
Just one thing, when you're finding max and min, should we just program our minds to just automatically f of prime of x set equal to 0, solve for x, because it looks like it's repetitive.
Yeah,
Okay.
all right. So let's take a look at one last thing, and that is let's set up for our surface area, right? The surface area is the thing we want to take the derivative of, set it equal to 0, solve for x. So let's grab our surface area equation, right? So we know that the surface area is 2 circles plus 1 rectangle, right? So 2 pi r squared plus 2 pi r h. I've got one variable on the left-hand side. This is kind of like my y. But on the other side, I have an r and an h, okay? This is very similar to the previous problem where we had length and width, and this was too many letters for us, okay? There is a way to solve it with this many letters, but that is for Calc 3, which is down the road. But right now we want to think, okay, how can I figure out how to get rid of one of the variables so that I turn it into something that looks much more familiar, like something with a y on one side, something with an x on the other side. And so I think I saw this idea in the chat earlier that we could get rid of one of these letters, okay? Now, if you could get rid of one of them, would you want to get rid of the R or the H? All right, what makes you say H? I think arguments could be made both ways, and I'm curious what makes you say H. Yeah, there's only one thing. Like if I want to substitute something in here, just like I put in that 200 minus 2L, I only need to sub it in one place. But if I tried to get rid of the R, I would have to put it in 2 places, and then I'd have to square that. That just seems like a lot more work than I want to. I already have to use algebra. Maybe I'm grumpy about that. So let me figure out the easiest, most efficient way to get to what I want, which is just to get rid of one letter, okay? So let's see, there's one piece of information that we have not used yet in our problem, okay? Like we had that 200 feet of fence, right? That was our limit. We only had 200 feet of fencing. What is our limit here? Like, what is the thing that's gonna make us say, oh, we can't get surface area bigger than a certain number?
1 liter.
Yeah, the 1 liter, exactly. Okay, so this 1 liter is actually going to help us with getting rid of that 1 letter. Okay, now it turns out though, when we measure like a height and a radius, do we measure that in liters? Like you're like, oh, the radius is a 1/2 a liter and the height is like a 1/4 of a liter. Is that how we measure radius and height?
No, we measure it in length.
Yeah, we measured it in length, all right? So what might be some more appropriate units for radius and height?
Centimeters, feet.
Great, exactly. We could use centimeters, we could use feet. All of those would be other ways of measuring radius and height. And it turns out in this case that 1 liter, right? Let's write this up here and I'll write it in red because I think it's pretty important. 1 liter is the same as 1,000 cubic centimeters. Okay, 1 liter is equal to 1,000 cubic centimeters. Now, a liter is also talking about how much volume is inside of a container. What that means is we can take this equation, this volume equation, and we can say, hey, we actually have 1,000 cubic centimeters, and that equals pi r squared h. And since I want to get rid of the h in the problem, I could get h all by itself in the volume formula. When I get h all by itself here, this is like how we were solving for the L. We can just divide over that pi r squared. So we get 1,000 over pi r squared. And everywhere we see an h in the equation we want, we can replace it with 1,000 over pi r squared. So down here in the blue, we're going to have 1,000 over pi r squared. All right, so let's make that substitution. Surface area equals 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Well, that looks pretty gross. I probably would want to see if I could clean this up a little bit before I take some derivatives, okay? So if we were to clean up things, we might still have our 2 pi r squared in the first term, but what does this become? Can we write this as a single fraction and reduce it? What does that look like?
2,000 over pi r squared. Or pi
Yeah,
r.
yeah. A bunch of things cancel out, right? The pi's, they cancel out. one of the radius cancels out. And so we end up with 2000 over r. Okay. Now, better yet, though, I'm going to be taking a derivative, right? Before I even got caught up in any of the algebra, I said, I want to find the derivative, I want to set it equal to 0, and I want to solve for x. I know I have to take this derivative. What might you suggest someone do with this second term so that they don't make that really easy mistake to make here? Yeah, we're going to rewrite this. 2 pi r squared plus 2000 r to the minus 1. Okay. I feel like students are like, do I have to do this? You don't have to do this, but if you take the derivative wrong here, I don't feel bad for you. You know what I mean? Like, these are all suggestions for common mistakes that I've seen through the years. So if you can look at this and know what the derivative is, great. But if you can't, and then you also choose not to write that out, I don't feel bad for you, right? And you shouldn't expect anyone to feel bad for you, because there's a way that you can avoid that mistake. And if that happens to be a mistake you tend to make a different choice, right? Figure out how to avoid that mistake. So we've got our surface area formula. Now we're ready to find the derivative, set it equal to 0, solve. So if I were to write the derivative of S prime or SA, I could say surface area prime. That's one way to write it. How would I write this using this notation? Like, what would go on the bottom here? What am I trying to take a derivative with respect to? Like, what's my x variable here?
R.
Yeah, so on the bottom, we're going to have dr. Okay. All right, let's find our derivatives. Derivatives of 2 pi r squared is going to give me 4 pi r. My derivative of 2000 r to the negative 1 is going to be negative 2000 r to the negative 2. All right, now I want to set this equal to 0. So I'm going to get 0 equals 4 pi r minus 2000 r to the minus 2. And again, here's another place where rewriting can help you work through the problem, right? A lot of times, if we're plugging in numbers for r, it's easier if we don't have that negative exponent. So maybe it's worth taking the time to write 0 equals 4 pi r minus 2000 over r squared. Okay, and that's a decision you have to make for yourself. If you don't feel like this helps you, you don't have to do it. But if you start from here and you make a bunch of wrong turns, I would suggest trying a different strategy, right? So it's all about like where you think you tend to make mistakes and how we can avoid those. How do I solve for r here? What's the algebra that we need to solve for r here? Yeah, let's add that to both sides. Great. So we've got 2000 over r squared equals 4 pi r. Great. What can we do from here? Yeah, let's multiply that denominator away, right? Fractions are gross. If we can get rid of them, let's get rid of them. All right. I argue in 2 steps, we can get r all by itself. What are those 2 steps? Yeah, divide by that 4 pi, and then what do we do to get r? Yeah, that cube root. Okay, so we're gonna have 2000 over 4 pi equals r cubed. And then r is gonna be the cube root of 2000 over 4 pi. And if you throw that into a calculator, you'll get about 5.42 centimeters. Okay. The calculus part to this problem appears in two places. Here, like the bigger structure, we find the minimum surface area, we got to use the derivative. And then to find the derivative here, that's literally the calculus part, right? Everything else is in that algebra and being flexible and thinking about how do I problem solve a problem that maybe I haven't seen before. Right? Now, this is one way to solve this. You certainly could have, at this point up here, multiplied both sides by r squared. That's absolutely fine. I believe you will still get to the same r value. Okay. All right, so let's go back and check. Did we fully answer the question? Right? It says, what dimensions will use the least amount of material? You write down r equals 5.42 and you lose the point. What did you lose a point for? Yeah, we didn't give the full dimensions, right? In order to tell someone the size of that can, we need to have the radius. We also need to have the height of the cylinder, okay? How do we find the height of the cylinder?
Solve for h by just plugging in r
Great, where are we plugging in r?
to our original surface area equals 2 pi r squared plus 2 pi r h.
But you don't know the surface area.
Oh, the volume.
Okay, better yet, we have a formula that tells us exactly what the height is. We got it from the volume, but in order to like substitute that we always end up with the equation that we need to help us find that other dimension at the end. All right, so yes, we are going to use this one because we have all the numbers, we have our radius, but this one, the one where we already isolated the h, that's going to be maybe the most straightforward way to get to our other dimension. Okay.
Oh, like how we did in example 1. Okay, I see what you mean.
Exactly. Right? I know it's weird for these two problems, like our pictures look so different, our formulas are so different, but at the end of the day, we follow like that same process, okay? So we can plug this into 1000 over pi r squared, and we should get about 10.84 centimeter, okay? And this, my friends, is our radius and our height. So that's all this is asking for. It didn't ask us to find the surface area, so we don't need to find that. All right, so you want to make sure you read the question carefully. Now, what I'm finding is some students are like, well, I'm just going to write everything for every question, even if it doesn't get asked for. Please make sure you read the question and make that decision. What do you need to write down? Right? That's part of the process, is like thinking about what you need to answer. Now, the cool thing about this is that it turns out that if you have a can and you want to maximize, you want your volume to be a certain amount and you want to use the least amount of material possible, if you have the height and you have the radius equals, and you have the radius, it turns out that the height will always be twice the radius. That will give you the least amount of material, right? I know we did this for a specific number, but it turns out this is true for like any volume relationship. You'll end up with the radius, and then the height will be 2 times that radius. And that will give you the least amount of material. Okay. So I think this question, like I said, is very similar to the Desmos activity that you're going to look at before Wednesday. Okay. The Desmos activity asks you slightly different questions and asks you to, actually plug in some numbers and things like that. But the flow of things should be pretty similar. And I think it's important to see it like more than one time and maybe in a more conceptual kind of way as well. Okay. So that is all we are going to take a look at today. All right. There are 2 other examples in here for you to take a look at that are sort of different flavors of the same kinds of question. But at the end of the day, you'll find that these sort of like 3 steps, like draw a diagram, formula brain dump, and finding that max min are going to be the same for any of these questions. Okay. All right, before we end class, do we have any questions for today?